Now, let's talk a little bit about inertia. Inertia, again, is that if you have something that's standing still, it will remain motionless unless you exert force on it. And if it's moving, it'll continue moving in a straight line with that speed, right? Unless it encounters friction or some other force and so on. Okay, the law of inertia gets two things. It'll remain in its state of motion. If it was standing still, it'll remain still. If it's moving with a certain constant velocity, it'll continue with that constant velocity. Unless there's a force on it. If there's a force, then there'll be an acceleration. Acceleration meaning it'll change the speed or change the direction. Now, if we drew a graph and we want to represent that law, let's say a picture of the trajectory of a particle. So let's say this is the x and the y, right? And we make x's like this and y over here. So if you have a particle standing over here, and it's just standing still and I'm not exerting any force on it, so the graph will just be a point, right? If it's moving, and it's moving like this, so I'll represent it like that. If it's moving like that, then I draw the trajectory like that. So the law of inertia is either it's a point or it's a straight line in this graph, right? Now, I want to do something a little bit more sophisticated and unite the two pictures. What I'm going to do is include time in my diagram. Instead of having only x and y, I'm going to limit my motion only to the x, so I don't need the y. I'm just going to have x motion. And I'm going to draw instead x and time. Now tell me, how would I draw the graph of this? Okay, what is the graph that represents this on this diagram? This is just standing here. Before, what was it? It was this dot, right? Because it's just at this point, x is not changing. Why? Okay, so the x is a line, a straight line, like this, because it will have the position x at this time, the position x at this time, position x at this time, right? A vertical line. Okay, does everybody see that? It's just a vertical line. This is called, the terminology is a worldline. Okay, this is when you draw it next. What happens if it's moving with a constant speed? What does the line look like? What does the graph look like? It'll be something like this, right? It'll be changing its x as it changes its t. The slope will be the same. Same amount of x per same amount of t, so a straight line at an angle. So how would you now formulate the law of inertia using this kind of concept? What would you say? Before we said the law of inertia is, in the xy diagram, it's either a point or a straight line at whatever slope. How would you reformulate it now? Tell me. Okay. How would you reformulate it now? You saw that instead of a point, it's a line, and this is also a line. However, either if it's standing still or if it's moving, it's a straight line. In other words, we could say that inertia is that particles have a straight world line. Okay? It's like a more economical, more sophisticated version of this. Particles have a straight world line, unless there's a force acting on them. If there's a force acting on them, what will the graph look like? Let's say it starts accelerating suddenly. Slows down, moves, goes backwards and forwards, picks up speed, stops. How would you draw that graph? It'll be more? Okay. The line is going to curve because the slope is going to change. The amount of x that it covers in a given amount of time will change. And then maybe it'll go back this way because the x will go back towards the negative, right? It'll move, it'll curve. Right? So the law of inertia is that the world line is straight if there's no forces. If there's a force, the world line is curved. So a very nice, concise way of talking about the law of inertia in terms of world line. Now, so we associate an acceleration always to a curved world line. Okay, and that's the key point. A straight world line means no acceleration, no forces. A curved world line of necessity means that there is some kind of a force. A curvature of the world line. Now, what is this curvature of the world line? Some of you have studied calculus. Okay. What is the first derivative of this? The slope, and that would be the velocity. The first derivative, let's say, of x with respect to t would be the speed, dx dt. What would be the second derivative of this? Would be the acceleration, and it's the slope of the slope, which basically gives you the curvature of the line. So, in other words, the acceleration, which is the second derivative of this graph, is also the curvature of the graph. So we have a very nice relationship between the acceleration of this particle due to a force on it and the curvature of the world line. Law of inertia. The world line would be a force is acting on it. Okay? Force is acting on it. Particle has a curved world line, and the curvature of that world line is basically the acceleration. F is equal to ma. The force that's exerted on a particle of mass m results in an acceleration a, or the acceleration due to a force F when applied on a particle of mass m. It's a beautiful equation when you think about it. If you go to it in depth, it's the simplest possible relationship between these three quantities. It's actually magnificent. Unfortunately, it's taught in such a way that people hate it and think it's trivial. Okay.